When nodes fall out of sync, a distributed system isn't just slow, it's actively lying to you. When managing large-scale LLM training clusters, the first major obstacle is ensuring all your weight checkpoint systems agree on the latest parameter states.
So we've talked about linearizability as one possible consistency model for distributed systems, which is a very strong consistency model, and we said it has the very appealing property that it actually makes a replicated system look as if it were not replicated. It looks as if there was only a single copy of the data and all of the operations on it are atomic, which makes linearizability a very easy to use consistency model. You basically don't have to think about the fact
if a single node falls behind, the entire gradient calculation drifts, eventually corrupting the model's convergence path. This leads to the ultimate eventual consistency lag, where write nodes and read nodes in your evaluation pipeline present completely different realities.
Hey everybody, it's Derek Martin from CodeOpinion.com. Eventual consistency is the term people most often use when referring to reading from a different data source than where they perform their write. This often leads to a bad user experience where a user performs some type of action and then doesn't immediately see the change in the UI. I'm going to explain the different ways this happens and how you can deal with it. This video is brought to you by EventStoreDB.
When an evaluation pipeline reads from a stale validation database, it makes false assumptions about the model's accuracy. Many junior MLOps engineers attempt to handle massive parallel datasets with basic synchronization steps, ignoring the underlying bottlenecks.
Problem was, what problems do distributed system solves, right? It's not easy to make junior developers understand that concept, especially for non-technical people to get into distributed systems. So we wanted to do something to let them understand this, and so we came up with the idea of talking like to a 5-year-old guy and see if we can try to teach something. But we started with a very simple requirement. So we asked them to...
Without structured, decoupled communication, your training jobs will run out of memory the second they face concurrency. As soon as your LLM pipeline spans multiple compute clusters, you step directly into deep waters with high complexity.
In your software, and you're in very deep water quite quickly, quite easily if you're not careful. And so there are some principles that matter a lot to be able to guide a design, to be able to cope with this explosion of complexity that you buy into as soon as you've got bits of software working on more than one computer in more than one panel.
Exactly. And so he felt that our folks needed to be...
It takes deep sympathy for the underlying platform to realize that you cannot simply scale outward indefinitely without consensus. What happens when you scale up your parameter servers and try to dynamically adjust the distributed hash ring on the fly?
That's the power of the hash table. But the problem is, the moment the size of the array changes, the hash table size changes, this all falls apart. Yeah? Because if blue, the key blue, used to fit in index number 11, if you increased or decreased the array size, and you know where I'm going with this, then the blue will fit into index 99 now. And as a result, right, you either won't find the value or you get...
Every single state change forces a complete data shuffle, causing immense network saturation and halting active training epochs. When you train an LLM on incomplete or inconsistent datasets, the system cannot announce its own internal biases.
But here is the problem. The data was incomplete, inconsistent, and sometimes duplicated. Hundreds of credit-worthy families were denied mortgage loans. Risk models failed. Some banks underestimated exposure. People lost their homes. Savings vanished. And markets crashed.
The models silently collapse from within, projecting a false sense of accuracy while delivering flawed outputs. To build a system that understands the world, we must realize it has to learn through a constant, rapid stream of data.
A little bit about the neocortex. It's a memory system. So if you think about it as a computer, forget it. It's not. It's a memory system. It's when you're born, it's a blank memory system, and as you grow up, you fill it up and you learn things. Now, it's a memory system that's attached to your senses, and you learn everything through your senses. You have from your eyes, the optic nerve is about 1 million fibers, your somatosensory nerve is about 1 million fibers, your auditory nerve is about 30,000. So you've got a couple million inputs going into your brain. They're fairly high velocity, not in computer terms, but
Just like the human brain, if the distributed inputs to the model are desynchronized, the cognitive model falls apart. Keeping model checkpoints secure across multiple nodes requires converting raw weights into safe, serialized blocks.
Network security. So how the cipher will apply? By using traditional block cipher structure. How the algorithm will be saved? How the algorithm will be implemented? We are taking one algorithm and we are converting or we are inserting it into a block. So within the block, everything will be executed. And coming to a block cipher is an encryption decryption scheme in which the plain text will be.
Any interruption in the serialization block ruins the checkpoint file, forcing the training run to restart from zero. Tracking training metrics across scattered clusters becomes incredibly complicated when you lack a single, unified source of truth.
Their parents, it really depends upon how you cut the data. And the core problem here for studying social mobility is a lack of large data sets in the United States that link parents to kids. So of course, in order to study what fraction of children are doing better than their parents, you need to be able to have data on both kids' earnings and parents' earnings in the same source. And that's something that we've lacked historically in America. So in a new paper that I'm...
Without linking metrics systematically, you end up with highly fragmented evaluations that hide critical model degradation. When a production desync ruins a live inference run, the only viable option is to take immediate, transparent action.
Now, the STAR technique is recognized by all hiring managers. It's a brilliant format to use when answering any type of behavioral interview question. And it allows you to easily remember your scenarios and your answers. And also, it will help you to get the highest scores possible for each answer to the behavioral interview questions. So we need to utilize this.
Documenting the replication lag and implementing robust retry mechanisms prevents the same error from repeating. The sheer compute required to run high throughput LLM pipelines has triggered an unprecedented digital gold rush.
Out of the market.
Not only are they driving away other businesses, data centers are driving up costs too. Pacific Power and Portland General Electric customers saw a 50% increase in their electricity bills since 2020. Analysts say that data center growth is a major factor. And what's worse, data centers aren't contributing as much money to the community as you might think. That's because Oregon's laws give data centers some $330 million a year in tax breaks.
But underestimating the actual energy and storage trade-offs of these giant setups is highly detrimental to any company. Building gigawatt-scale infrastructure sounds spectacular until you confront the extreme physical demands of keeping those clusters running.
The world's largest data center.
We plan to establish gigawatt-scale AI-ready data centers in Jamnagar.
It is our goal in the new information and technology age to make Jamnagar a leader of the world.
And to me, this is just the starting.
Similarly, Gautam Adani is about to spend $10 billion into building data centers across Andhra Pradesh, Gujarat, and Tamil Nadu. And while most people think this is India embracing the AI revolution,
massive data pipelines require continuous power, creating a severe strain on surrounding resources and infrastructure. Operating high-stakes AI models means you have to constantly monitor, validate, then protect the data streams.
I have to go out and discover where all this stuff is. I need to look in my databases. I need to look in my files. That's structured sources and unstructured sources of data. Also, I want to look across my network. Sometimes information is flying around and I'm not aware that that might be sensitive stuff that's leaving my network. That becomes particularly important. Then what's next? Well, then I need to do some protection. How am I going to protect
If unauthorized or corrupt inputs penetrate your training loops, the security of the entire model architecture is compromised. When managing long, intensive compute tasks, sometimes the hardware throws sudden, unexpected anxiety attacks.
I had anxiety attacks and panic attacks, and it was actually long. That it was a long time that I wasn't having them. So yesterday was a bit rough, but nothing that a good dose of sleep couldn't fix. I actually like this one. If you'd like to, sorry.
Having robust backup systems ensures that a brief physical disruption doesn't ruin weeks of active compute. Achieving complete line erasability in distributed databases is incredibly expensive due to the massive message volume.
Are atomic, which makes linearizability a very easy to use consistency model. You basically don't have to think about the fact that your system is distributed, and it just kind of works in the way you might expect. Unfortunately, it comes at a price as well, so linearizability is not actually suitable in all possible circumstances, for several reasons. One possible reason is that it's actually quite expensive to implement. If you look at the protocols that we discussed, there are lots of messages going.
Forcing strict consistency across all nodes introduces severe latency bottlenecks that stall real-time MLOps queries. When a model writes a state change to the primary node, it immediately races against the replica synchronization.
This is with replication lag. We're going to use a read replica from whatever primary database you're using, and that replication is eventually consistent. So what happens is we have our client that it makes a request to change some state, perform some type of action, some type of command, and we hit our primary database for reading, potentially, and writing. So we perform that, and we return back to our UI, and maybe our UI then immediately goes to try to fetch that data that it changed in some way. So it then makes
this brief window of replication lag allows stale data to bypass validations and trigger false inference decisions. Assuming all your servers share an identical global clock is a fatal mistake in high-frequency distributed operations.
This problem we pointed out during the review for this architecture was, what happens if we have dozens of concurrent uploads? So it was pretty easy. We start uploading and processing a few large files, and we run out of memory. So after that, the most advanced junior developers in the course said, OK, great. So why don't we just take a load balancer? We create a couple of servers, and if one is busy, we can redirect.
Latency and physics make absolute synchronization impossible, meaning our designs must never rely on timestamps alone. To manage distributed desync, you often designate a single leader node to coordinate the right path.
A good sense of how they work, because without that, you don't know how to utilize them properly. You don't know how to debug problems. I wouldn't necessarily call it mechanical sympathy, because you're not getting down to the hardware level, but you do need some sympathy with the underlying platform that you're working with, a kind of platformish sympathy to be able to, times when you need to focus on performance or the way that things are operating.
Yeah.
Go ahead. Yep.
Sorry, I didn't.
But if the leader goes down under heavy load, your system faces a chaotic re-election phase that blocks active writes. MLOps engineers often attempt to vertically scale their systems to extreme limits to avoid distributed system problems.
So why I'm mentioning that? The problem that we are seeing today with distributed system is as follows. If my database are increasing in size and it no longer can fit in a single instance, I bumped up the vertical scaling to its maximum. It's now 48 core CPU, 3 gigahertz, whatever, it's 512 gigabyte or even 1 terabyte RAM, but it's still, I have billions of rows.
But eventually, even a terabyte scale machine collapses under the sheer volume of high concurrency LLM logs. Relying on biased, Inconsistent data records causes automated systems to make silently disastrous decisions.
The problem was with the data. Some revenue was recorded too early. Some costs were not fully captured. When it comes to individually, they seemed minor, but together, they painted a false picture of success. When the truth came out, stock crashed, executives resigned, and the public trust collapsed.
The subsequent damage to organizational reputation is massive, yet no one notices the silent failure at first. A highly capable model must learn everything through a fast, continuous influx of sensory information.
Milliseconds. So you've got this fast data stream coming into the brain. The brain has to build a model of the world. When you're born, you don't know about things like Google. You don't know about buildings and chairs and cars and computers and operating systems and bananas, none of this stuff. You have to learn everything. It's an amazing amount of stuff, and you have to learn it through this fast stream of data coming in. And so the New York Cortex builds a model of the world, and from that model it does three basic things. It makes predictions about future events. It says, hey, given my current state...
It constructs predictions based on its training, but if the incoming metrics are corrupt, the predictions fail. Distributing plain text across a parallel matrix requires dividing the information into highly structured, equal halves.
Divide this information into equal parts or two halves, that is left part and another one is right side part. Now you are taking the left part and you are taking the right part. Here you are taking keys. So here I am taking one key and I am applying in this fiscal structure. So where K is the key, R is the right hand side of the data. Here I am taking the plain text and that divided into two parts. So
shifting positions back and forth ensures the model parameters remain secure, preventing rot raining leakage. Rebuilding absolute metrics across several generations of training models requires linking parent-to-child records perfectly.
Nathan Hendren and others, we solved this serious data problem by combining census and CPS data back to 1940 with recent data from de-identified tax records. And that methodology that we develop allows us to estimate the fraction of children who earn more than their parents going back to the 1940 birth cohort. So let me show you what we find in a series of figures. So I'll start with this here, which shows you the percent.
Historically, this lack of matched data sets has made it incredibly difficult to draw accurate long-term conclusions. When team members went offline due to sudden sickness, we had to adapt our workflow to keep the pipeline intact.
Now, although I felt the criticism was unfair, simply because I was trying to help the company, it was my task to take on board his feedback to improve. Now, I explained to my manager that I was trying to improve customer relations, but that I fully understood there was a need to act with speed because other customers were waiting on the line that also needed my assistance. Now, after reflecting on my performance, I made changes as per my manager's instructions, and this improved the speed of my call.
Taking proactive, unselfish ownership of the pipeline desync allows the team to correct course without losing momentum. Communities rolling out tax incentives to attract data centers often find the real benefits are highly temporary.
Busy. It was a really good idea. I make a lot of money. It was great. But I don't know if it's going to last very long. I think after we get them up, they don't need us anymore.
Ashley says her husband works on data centers too, but not in Oregon. He's nearly 2,000 miles away in Abilene, Texas.
My husband decided to go work in Abilene, one of the biggest data centers built in the country. Big as all of the data centers here in Hillsboro combined into one.
To find out more about what these jobs are really like, I decided to head to Abilene myself.
Once the massive hardware is built, the high-paying construction jobs vanish, leaving behind strained local resources. Storing critical data on foreign servers exposes your most sensitive model pipelines to external surveillance.
Data centers can bleed an entire city dry. Like I said, in the US, an average 100 megawatt data center uses more power than 75,000 US homes combined, and it consumes 2 million liters of water every single day, which is again equal to the water usage of 6,500 US households. And most of them use drinking water for cooling. And now these data centers are coming up in Navi Mumbai.
This creates massive vulnerabilities to espionage or blackmail, undermining national security and data sovereignty. Securing your checkpoints means you must store keys in a system that generates them randomly.
If I encrypt the data and lose the keys, then I lose the data. So I have to have a key management system that generates keys securely and randomly, that stores them and keeps them secure, that tells me when I need to rotate keys and put new keys in place. So that key management system is particularly important. I also need access controls, the ability to say who gets access to this and who doesn't. We could use things like multi-factor authentication, which I've talked about in other videos. And then backup, the ability.
If you encrypt the model weights but lose track of your rotation schedules, you lose the entire data set. Allowing stagnant data of pipelines to sit unmonitored leads to an internal contamination that is impossible to clean.
Because I realized that inside I call it peak, I don't know how you call it. Inside, there's actually a hole inside this up. There is a hole, and it's molding, and I can't clean it. And I don't want to drink mold.
Just like physical mold, bad data degrades the system, eventually forcing a complete rebuild of the processing pipeline. When a distributed system faces a partition, some nodes find themselves completely unable to reach a consensus.
Reasons. One possible reason is that it's actually quite expensive to implement. If you looked at the protocols that we discussed, there are lots of messages going back and forth, lots of waiting for responses, probably something like around 2 round trips for most requests. So, it's just going to be a bit slow, basically. Another limitation is the scalability, potentially. It depends a bit on the exact algorithm you're using, but if you're using a consensus...
In those moments, you are forced to choose between maintaining strict line erasability or dropping availability entirely. To bypass the latency of database polling, modern MLOps pipelines push events directly to the client.
So what happens is we have our client, it's making a request, some type of command to make some state change. Maybe we have a domain model and we're publishing an event and we're persisting that to our event store. So we're event sourcing, we have our event store, then we return back to the client saying, yes, your command succeeded, wonderful. Then again, it tries to, at some point, your UI immediately then goes to perform a query trying to hit your projection, your query.
This event-driven approach ensures that the user is immediately notified of state changes as soon as they occur. When trust in your data architecture is lost, decision-making reverts to sheer guessing, endangering the entire organization.